So welcome everyone for the follow-up video of Analemma, in which we will talk about the mathematics behind the equation of time. Although this is a beginner's video, but some of the mathematics could be challenging, so we encourage students and teachers to also go through some of the supplementary resources that we will point out. So let's begin. So let us consider a simplistic scenario where Earth orbits in exactly circular orbit. There is no obliquity as well, and there are no time zones. So if we start from position of Earth, where for the observer the sun is at the culmination, the sidereal rotation of Earth is 23 hours 56 minutes, but after 23 hours 56 minutes the sun will no longer be at culmination. As you can see from this diagram, it will not point towards the sun, but it will take another 4 minutes to now point towards the sun. Now in such scenario where there is no obliquity, at equator when sun is at the zenith, after exactly 24 hours sun will be at zenith again, and so on and so forth, and this will continue. However, because Earth's orbit is not circular, it is elliptical and follows Kepler's law, sometimes the angular velocity of the planet is fast compared to its average angular speed, and sometimes it is slow. Let us consider what happens when angular velocity is fast. So let's say Earth is near perihelion, it will in the same 23:56 minute, it will move along the orbit at a larger distance, let's say somewhere over here, and now for it to point towards sun again from culmination to culmination, now it has to rotate somewhat extra. Now what will happen exactly at 24 hour, sun will slightly be behind because it has to rotate for some more time to now be at culmination again, and that some extra time comes from our equation of time calculation. So in order to understand in more details how different components affect equation of time and analemma, let us start with orbital motion of the planet. Let us refresh ourselves with some of the concept. We know that the planet will orbit or move along the elliptical path where the sun will be at one of the foci, and if it is at some arbitrary position, let's say B in this diagram, we could define true anomaly as angle between perihelion, focus and that planetary position. For eccentric anomaly, some of the students make this mistake to intuitively consider B, origin and the perihelion, but we define it in slightly different way. First we have to project this position into a circle that has the same radius as semi-major axis. The angle made by this projected position with origin and perihelion, this is called eccentric anomaly. Another thing to note is both of these angles can be defined for any ellipticity regardless of a planet is orbiting or not. This has nothing to do with Keplerian motion yet, but when orbital motions are to be studied, we introduce one more anomaly, that is the mean anomaly. So we know planet will not move along the orbit at a constant speed, but if there exists a body that moves along orbit at a uniform speed, or one could say there is no eccentricity at all, then both the true anomaly and eccentric anomaly for zero eccentricity will be same. That same value is considered the mean anomaly, right. So when we introduce Keplerian motion, we know that planet sweeps equal area in equal time interval. So that leads to a situation where planet does not move along constant angular speed. Around perihelion, its orbital speed is quite fast. At aphelion, it's relatively slow, but there is a relation between all the angles we have talked so far. Again, if we refresh, this green angle is our eccentric angle, the angle between the projected position, origin and perihelion. The eccentric angle will be 0 when planet is at perihelion, and similarly the true anomaly, perihelion, sun and the planet, and this again will be 0 for perihelion and it will be 180 for aphelion. Now what we have done, we have introduced another body that has the same period of that of the planet, but moves with a constant angular velocity in a circular path. This angle, perihelion, origin, hypothetical body, that is our mean anomaly, and mean anomaly changes uniformly through time. That is why mean anomaly you can very easily write it as 2 pi by p times t, but we could see eccentric anomaly and true anomaly, they do not have this uniform behavior, rather they follow this equation. So, given the eccentricity of the orbit for a given mean anomaly, which is very easy to calculate, one could find what will be the eccentric anomaly at that time. Now, as simple this equation seems like, it requires some sophisticated calculations to solve this. We will not go in detail in this video. However, if we know the time, we know eccentricity, with some complicated methods, we can know what the eccentric anomaly is. So, the next step is we have to calculate what the true anomaly is, or what we could do for small eccentricity, we could do a Taylor series like expansion. We could approximate eccentric anomaly with this infinite series, and if eccentricity is too small, we could remove higher order terms or even the e square term, depending on how small the eccentricity is. Then this becomes fairly easy to work with, and once you have the eccentric anomaly with this geometrical relation, you can also find the true anomaly. Now, the way we define the equation of time is the difference in mean anomaly and true anomaly. Okay. So, true anomaly could be considered as position of sun, although we define true anomaly angle seen from a bird's eye view, but if you want to relate this with where the sun will be as seen from earth, you have to make some appropriate transformation. You could also consider this as the time difference between ecliptic longitude and right ascension, or the time difference between the sundial time and your clock time, as your clock time moves uniformly. So, that can be considered as something related to mean anomaly. Sundial relies on where the true position of sun is. So, all these things are interrelated. So, if there was no eccentricity and no obliquity at all, the right ascension of the sun would move uniformly throughout the year in celestial sphere, but because of factors we will discuss, that is not the case. In this animation, we have exaggerated the eccentricity of the planetary orbit. Here the purple dot moves along the celestial equator uniformly. We have assumed no obliquity, it moves with the uniform speed. However, because planet orbits at a varying speed, the sun as observed from the planet also moves with the varying speed. So, at some point it is behind, at some point it is ahead, and that is also what we see in this equation of time. So, as we have already discussed, when the orbital speed is high, the sun will fall behind, because that is how solar days are defined. We see equation of time going in negative direction. At perihelion, if it was 0, again at aphelion it is same, it crosses 0 again. This time equation of time is ahead, so you have to subtract this much time from the solar time and you get your equation. Although this is quite exaggerated, case of earth eccentricity is small, it varies only plus minus around 8 minutes. So, when we come back to realistic scenario, but we ignore the obliquity, we see that roughly 7.5 minutes plus and minus there is a time difference. So, if there would have been no obliquity at all, your shortest shadow, instead of being at 12 noon, will be sometimes at 12:07 p.m. or roughly 11:53 a.m. or so on. You could also write it down as this equation as a sinusoidal behavior. If you plug in all the orbital values of earth, we get this equation as -7 times sine of d, where d is number of days since perihelion. So, at perihelion it would be 0 and it will have a sinusoidal behavior. Now, let us consider the second major factor, that is the obliquity. So, over here we have considered that there is no eccentricity at all. We notice that even though sun would move along the ecliptic at a uniform speed, the declination and right ascension are no longer uniform. Let us take declination for example. Although if we know the ecliptic longitude, we have seen in previous video how we can transform ecliptic coordinates to spherical coordinates. If you prefer more Cartesian based understanding, we can look at that as well. So, let us say sun was moving in a uniform speed on a unit circle. If there was no obliquity, those 3D coordinates will be cos theta comma sin theta, and as theta varies, sun will move along the celestial equator. Now, instead when we introduce obliquity angle epsilon, then this coordinates become cos theta comma sin theta cos epsilon comma sin theta sin epsilon. Now, the position of sun as seen from earth will be a function of true anomaly, but because it is the sun as seen from Earth, we have to make some slight modification. Also, true anomaly is 0 at perihelion. Usually we measure spherical coordinates are 0 at vernal equinox. So, if you make this correct transformation, could have this modified true anomaly as part of this equation. So, as things move uniformly, how it affects the declination and right ascension. The z coordinates as defined in this diagram will affect its declination. So, we can easily see sine of declination will be sine of epsilon times sine of ecliptic longitude, let us say. If for Earth like case where the obliquity angle is small, although 23.5 degrees sounds like a larger number, but in radians it is small enough to apply sin x equal to x approximation, and we can write it in a much more simpler neat form, and we see declination follows a sinusoidal like behavior. However, in previous video we have also seen if epsilon is quite large, this is no longer sinusoidal. Now, what about the right ascension? From similar coordinates we can also realize the tan of right ascension will follow similar coordinates. You can club sin and cos with the tan of longitude, and true anomaly moves uniformly, right ascension will not, and we can see this from this animation that the array of sun is sometimes behind that of the mean sun, that is this purple dot that moves at the uniform speed. Sometimes the sun is ahead, sometimes the sun is behind, and that follows sinusoidal like behavior with twice the frequency. So, at vernal equinox it is 0. As the declination increases from vernal equinox, the equation of time also increases, and it becomes 0 at summer solstice and again 0 at vernal equinox, then at winter solstice, and so on and so forth, and this is how the equation of time varies. This could also be approximated equation of time entirely due to obliquity as around 10 times sine of 2d, where d is number of days since vernal equinox. In the previous effect it was since perihelion, over here it is around vernal equinox. This will give equation of time in minutes. So, if we combine both these effects, we get our equation of time, but we have to include third and the most important point, that is which we also talked about in the previous video, the difference in ecliptic longitude between the perihelion and vernal equinox. If we adjust both of these factors and align them, let us say at 1st January, perihelion occurs roughly around 3rd January. We see from 3rd January it goes down, aphelion again crosses 0 and comes back. Vernal equinox is roughly around 20th March. We see this effect. Once properly aligned and added, we get this equation and we get our equation of time. This term is due to the longitudinal difference between perihelion and vernal equinox. Although we have discussed the importance of where the effect crosses the 0 point, in this combined effect the 0 points do not hold that much of a value, but if those values are, let us say, known, you would know that at these days the sundial time is same as the clock time. So, if we recall what we have learned so far, had the sun follow the mean anomaly entirely, that is there was no eccentricity and no obliquity, we would see sun rise every day at the same time, culminates at the same time and sets. So, if you were at equator, you would see sun exactly overhead at noon time every day at the same time. It will be a 0 shadow day every day. Any other place on earth you would not see such effect. The sun would never be overhead any other place throughout the year, but the two effects we have talked about, the eccentricity and the obliquity, that changes the declination and the right ascension of the sun. So, therefore, if we observe sun every day at the same clock time, we see that the declination compared to the previous days and right ascensions have changed, and they change in such a fashion that we get this 8 like figure that we call analemma. Again, important note, do not observe sun without proper arrangements and protections, they could hurt your eyes or your equipments. A simpler way would be to observe how the shadow of, let us say, a vertical stick at the same time and the same location, you would also see the similar analemma type effect. In this animation we also see the daily motion of the sun. So, sun rises at some particular azimuth which is not always at 90° east, follows a path roughly parallel to the celestial equator, and then sets at some azimuth which is also not always 270° east or the west cardinal point. This is due to the both of these effects we have studied so far, the eccentricity and the obliquity. If we would like to predict when the sunrise and sunset time would be, we also have to take into account the equation of time. Even though this is a beginner video, we have introduced some of the advanced mathematics as well. So, what we would encourage students and teachers to do is to follow a link which will also be made available in the description, is how affecting the different parameters like the eccentricity, obliquity and the vernal equinox position changes our analemma like pattern. We could also do this for different planets. Okay. Few things to note, because we assume planet moves in Keplerian orbit, wherever these things will not hold, for example in Pluto and Charon system, one has to be careful. And also in this video we have ignored any higher order effects. So, if you actually go to a different planet and the analemma does not match, do not worry, you probably forgot to introduce the higher order effects. We conclude with the final note that since the obliquity, the eccentricity and the longitudinal difference of perihelion and vernal equinox keep changing because of various other factors, the analemma will not remain constant. In fact, around year 6400, both the lobes will roughly be equal. They will flip if you would observe them in year 11,000 and so on. Most of the people of the production house will no longer be available to verify this claim. So, if this video survive till the year 11,000, hi, I am Akshat from year 2024. This is our claim based on the simplistic understanding of analemma. In case the analemma of this year does not match this, do contact our future production team. I am sure they will be able to assist you. That is all from this video. If you have any doubts, any comments, or there is any topic you would like more detailed video on, do let us know in the comments. Thank you.